Hello everyone, my name is Vinay. I'm a PhD student in the EC department IISc, advised by Professor Naveen Kashyap. Today I'll be talking about my research on probabilistic forwarding with coding for network applied broadcast. Before I begin, I should thank Cisco for funding most of my PhD. And also I'm currently in the job market, looking for research position either in the academia or the industry. Please feel free to contact me at this email address if you have any openings. Let me begin with the motivation for my talk. Let's suppose you have a field in which there are sensor nodes deployed. These could be temperature or humidity sensors which form a network. Let's suppose there's a particular node designated as a source which has some information that it needs to broadcast. For example, it would want to update the sensing frequency of the nodes. An alternative example that you can have in mind is that of Internet of Things, where the source wants to do over-the-air programming of the IoT nodes. In both these scenarios, the nodes have the following constraints. They are energy constrained, they have no knowledge of the network topology, and they have limited computational capability. In this scenario, we would want to propose a broadcast algorithm which is lightweight, low complexity, and saves energy. A naive algorithm for broadcasting is what is called as flooding. Let me explain this using this small graph. Let's suppose the source has two packets. The source is the yellow node here, packet 1 and packet 2. Packet 1 has information X and packet 2 has information Y. In flooding, whenever a node receives a packet, it just transmits to all its neighbors blindly. And this it does for each and every packet. So here, since there are 4 nodes and there are 2 packets, there are totally 8 transmissions. More generally, in a large network of n nodes, with the source having k data packets that it wants to broadcast, there are a total number of k times n number of transmissions. However, notice here that a large number of transmissions are redundant since a particular node receives the same packet from multiple neighbors. This is not energy efficient. Now, to overcome this, an alternative that has been proposed in the literature is what is called as probabilistic forwarding. Let us go back to our example of the small graph. Here again, the 2 packets X and Y. Now, upon reception of a particular packet, a node tosses a coin with some probability P. If it lands heads, it decides to transmit the packet. If it lands tails, it does not transmit the packet. It does the same independently with other packets, independently of the other nodes as well. Here, notice that because of our probabilistic scheme, there are only 6 transmissions, the yellow node corresponding to the yellow nodes here. However, probabilistic forwarding comes with its own problems. For example, let's suppose the first packet transmission is as before, whereas in the second packet transmissions, both these nodes toss tails. Now, the node on top will not receive the packet at all, and hence it is lost the transmissions from the source. More generally, if on a large network of n nodes with k data packets and forwarding probability of p, there are at most k times n times p number of transmissions in the network. Now, for a non-trivial probability p, this is certainly lesser than the number of transmissions that were used for flooding. However, notice here that the red fraction of nodes are those that did not receive the packet at all. In order to improve upon the fraction of nodes that receive the packet, we introduce probabilistic forwarding along with coding. Let's go back to our example of the 2 packets X and Y. In packet 1, all the nodes receive the packet information X from the source, whereas in packet 2, suppose both these nodes toss tails, then the node on top does not receive the packet. Now, to overcome this, initially the source encodes another packet with the information X plus Y and transmits it to all its neighbors. All the neighbors of the node again follow the probabilistic forwarding protocol. Notice here that encoding in such a way ensures that any node upon reception of just 2 out of these 3 packets will be able to retrieve both X and Y. Now, the transmission of the third packet happens as in the probabilistic forwarding case. Now, the node on top receives this third packet. The node on top now has the packet 1 and packet 3 with information x and x plus y, and it can retrieve y from this. Again, there are 6 transmissions here. More generally, the source encodes k data packets into n-coded packets such that any node upon reception of at least k out of the n-coded packets is able to retrieve the information that the source intended to broadcast, that is, the information contained in the k data packets. Such codes are used in practice as well. For example, maximum distance separation codes, foreign codes, etc. More formally, a problem statement looks this way. We are given a graph with n nodes with the k data packets being encoded into n-coded packets by the source. We are given a delta close to 0 and a retransmission probability p. Let us define this Rkn to be the number of nodes that receive at least k out of the n-coded packets. Since we are interested in the broadcast problem, we are basically interested in the minimum forwarding probability such that the expected fraction of successful receivers is at least 1 minus delta. This Rkn by n is the fraction of successful receivers. The performance metric that we are interested in is the expected total number of transmissions when the forwarding happens at the forwarding probability pk and delta. Our interest is mostly on what happens on random geometric graphs, since random geometric graphs are used to model ad hoc networks, the kind that we had seen in the beginning. But what are random geometric graphs? These are just a bunch of nodes deployed in an area at random and connected, and any two nodes are being connected if they are close to each other. We observed that on most well-connected graphs, such as these random geometric graphs, grids, or other lattice structures, the performance of the probabilistic forwarding with coding behaves something like this. Here, the top graph is the minimum forwarding probability pk and delta, and the bottom graph is the total number of transmissions, tau k and delta. Here, k was equal to 100 packets, and the x-axis on both these plots is the number of coded packets n, varying from 100 to 200. Let us look at the second graph first. Notice here that the red point that is indicated here corresponds to the point where there is no coding, that is k equal to n equal to 100. Now, the number of transmissions is decreasing as you increase the number of coded packets. This means that there is a benefit to coding along with probabilistic forwarding. Moreover, the point of minimum, that is the point corresponding to this minimum, the number of coded packets and the corresponding forwarding probability corresponding to this minimum is the ideal parameters for operating the network in order to have maximum energy benefits at the same time achieving the broadcast. However, this behavior is not seen on trees. For example, let's consider a binary tree with the root node being the source. Now here again, the plots of the forwarding probability and the total number of transmissions are provided. Here you can observe that the total number of transmissions increases with the number of coded packets, saying that there is no benefit to coding. This is because of the following fact. Notice that on a binary tree, a large fraction of the nodes reside on the leaves. For example, for a leaf node to receive the packet from the source, all the nodes on the unique path joining the source to the leaf needs to broadcast the packet. Now this requires a very high probability, as can be seen in the first plot here. The forwarding probabilities are very close to 1. Hence, even though there are additional packets being added, each packet is being forwarded at the same probability. Thus, there is no advantage to adding these extra packets. Now, whereas in the case of a grid, for a packet to be received by any node, there are multiple paths, and hence one can afford to transmit at a very less probability while still ensuring that the node receives the packet. This is why we see there is a decrease. The probability values involved in the grid are much lesser. This offsets the additional number of packets that are being added. However, a formal proof of this fact involves the theory of percolation and the ergodic theory. In conclusion, for the examples that we had in the beginning, these form dense networks, and hence employing coding with probabilistic forwarding gives us significant energy benefits. That's all for now. Thank you.